All right, we've got another real world scenario to take our ability to assess rates of change with equations involving variables that are changing with respect to time and putting it to use in a real world situation. So here, imagine a spy is watching a rocket launch from a position 5,000 meters away from the launch site. As is always the case with these problems, pictures are super valuable. So let's try to imagine the situation. The spy is watching a rocket launch. So here's a rocket that's launching. Here is our spy. Our spy is watching it from a position that is 5,000 meters away from the launch site along the ground. So here the spy is 5,000 meters away. As we saw in the last example, and as we tend to do traditionally, let's just call that measure x, the horizontal measure. That would seem to make sense. Okay, now, if the angle of elevation between the spy and the rocket is changing at a rate of 0.2 radians per second, imagine here, as the rocket is rising, that angle theta between him and the rocket, that's going to be changing. And imagine that angle is changing at a rate of 0.2 radians per second. You can actually see in the unit here, this is a unit with respect to some change in time, and in particular, this is a unit of d theta, dt. The change in the theta, the change in the radians with respect to time, 0.2. Note, it should be a positive number, right? Because as the rocket goes up, the angle is going to be growing. That rate of change is occurring precisely when the angle of elevation is pi over 6. So this is going to be at the instant that our angle of interest is pi over 6. Okay, that's going to be helpful to us as well. I tell you what, I'll put this in black so it jumps out a little bit better. But the long story short is, because you could imagine the change in the angle could be different at different instances in time, right? Maybe when the rocket's getting off the launch pad, it's going fairly slowly, but then at some point it starts speeding up more. So at different angle measures, you might have different rates of change of your angle, but the speed at which your angle is changing is being measured precisely at this instant when the angle of elevation is pi over 6. Okay, now here's the question. This would be something that if you could imagine back in like the 1960s during the space race, this could be something that the spy would be very interested in knowing. What's the vertical speed of the rocket? Because if you imagine back in the space race, the Americans and the Russians in the 1960s, who was going to get to the moon first was a very big deal. So knowing how fast the Russian rockets were relative to how fast you knew your rockets were would be really good information. But of course you couldn't just go to them and ask them for that information. But you see, if you knew how far away you were when you saw the rocket launch and you were measuring the angle's rate of change, you could then extrapolate how fast the rocket was indeed moving, which would, well, give you good information to bring back home. So we're going to do that exact same thing here. We want to know how fast the rocket is moving. Now, vertically, right? We're thinking of this vertically. So let's just call this distance y here, the vertical distance. And what we are after, what we are trying to find, is change in y over change in time. We want to know how fast the y is changing with respect to time. And I claim we can totally do it based on the information that we've got here. We've got information about angle, we've got information about horizontal distance, and we've got information about vertical distance. In particular, since the horizontal and the vertical meet at a 90-degree angle, then we can say, okay, do we have a way to relate an angle to an x and a y? Do we have a way to relate an angle to an adjacent side and an opposite side in a right triangle? Yes, we do, right? We can say the tangent of our angle is equal to y over x. The tangent of our angle is equal to the opposite over the adjacent. Now we've got a relation between our theta, our y, our x, and now we can play calculus to get our d theta, our dy involved. Okay, so take the derivative of this guy. Derivative on the left-hand side, secant squared theta, but we took a derivative with respect to theta, so we tap on a d theta. That theta is respect to time, so we put a dt in as well. The right-hand side, we're going to need the quotient rule for this, but so be it. We can use the quotient rule. This is going to be the derivative of y, that's 1, times x, but that was the derivative of y. And then a minus sign, excuse me. And now we're going to take a carbon copy of the first times the derivative of the second. But the derivative of the second was a derivative with respect to x. And this is all going to be over the denominator squared. But now when you look at this, we are trying to find the dy over dt. So if we can use r theta and plug it in, we'll have one less thing to have to find. If we can put in a d theta dt, which we know, that's one less thing we're going to need. Put in the x, that's one less variable in our expression. Do we know the y? We don't have the y, but I claim we can figure it out. We can put the y in there, put the x downstairs squared, and then multiply by the whatever dx over dt is. If we can get everything besides dy over dt discovered and input, then the only thing left is to compute dy over dt. So let's look at the information that we have. We know that our theta is pi over 6. So we've got secant squared pi over 6. D theta dt, that's 0.2. So that is the number that is. On the other side, we got 1 times x, but heck, we know x is 5,000. What about dy over dt? Well, actually, that's what we're trying to figure out, so we expect that to be left over. And in fact, we want that to be the only thing involving letters that is left over. What is y? Now that's going to take a little bit of work, because we don't know what y is exactly. We know we're 5,000 meters away. We know our angle of elevation is pi over 6, but what is our y? Now, if we need to know y is not a statement related to calculus, that's just the good old-fashioned variable. We could go to our original relation. Since we know that our angle is pi over 6, and we know that tangent is always equal to y over x, well then we can solve for our y, because here our y is just going to be 5,000 times whatever the tangent of pi over 6 is. And as it turns out, the tangent to pi over 6 is square root 3 over 3. So the y here is going to be 5,000 square root 3 divided by 3. Or I suppose if we run this number to get it down to like a more computable, digestible size, let's run the number. Okay, so 5,000 square root 3. And then we're going to take that number and we're going to divide by 3. Sweet. Okay, so that number is 2,866.75 more or less. That's approximate, but so be it. But we know our y is 2,886.75. Sweet. Okay, we're going to plug that in, because now that's one less variable in our expression. We've got y 2,886.75 times the 1 times the dx over dt. What is dx over dt? Dx over dt is how the x is changing with respect to time. How is the x changing? I mean, that rocket is shooting straight up. So the x is not moving. Our guy is sitting there watching the rocket going up. The rocket is going straight up. The long story short is we can then know that our dx dt is 0. That is not changing. And in fact, as soon as we have that, then, fortunately for us, that 2,886.75 number drops out because it's being multiplied by 0. And now this is just over x squared, which is 5,000 squared. And in fact, when you look at this now, you can see that the 5,000 that is upstairs is going to cancel with one of the 5,000s downstairs. And then in order to get dy over dt by itself, we're going to have to get this 5,000 to the other side, but you can get a 5,000 in the denominator to the other side by just multiplying both sides by 5,000. And the long story short then is upon all of that computation, you get dy over dt by itself, and dy over dt is merely equal to 5,000 times secant squared of pi over 6 times 0.2, which rephrased differently, secant squared is just 1 over cosine squared. Now that's something you could do in a calculator, times 0.2. What is cosine squared of pi over 6? That is, what, 3/4, so 1 over that would be 4/3. Long story short, this comes out to be 5,000 times 4/3 times 0.2. And well, if we run the numbers there, we get 5,000 times 4 divided by 3 times 0.2. Ah, beautiful. We get a number, that number, 133.33. Now what units does that have? Because this is vital information. I mean, if you're going to be the spy and you're going to tell the president how fast the rocket was rising, you better be able to give a unit so that number has clarity. This is the change in y over time. What were we measuring y in? Well, we measured x in meters, so y correspondingly would be measured in meters. And then the question is, what's the time unit? Well, we were measuring our change in theta in terms of radians per second, so this is meters per second. And now, we know precisely how fast the rocket was moving. The rocket was moving at 133.33 meters per second. And we got all of this information simply by knowing how far we were away from the launch site, something that you very well could know if you were spying on a rocket, and how fast the angle was changing as the rocket was rising, something else you could very well know if you were watching the rocket from afar. And we did it all using calculus and our knowledge of how to relate rates when the variables are changing with respect to time.